Alright, well, let's get started. Welcome aboard. My name is Stephen Wylie, and I'm presenting using artificial intelligence with augmented reality. And to give you a little bit of info about myself, I'm a Google developer expert in machine learning, hailing from Dallas. As side projects, I like to explore arcade machines, pinballs, and computers of all eras, and kind of spare time, whenever I have left over, I like to watch game shows or also do fancy dress-ups. So, incidentally, I also have a lot of patents in this area. I got 6 on augmented reality and then 1 more on kind of an application-specific implementation. So, does anybody actually do this kind of stuff themselves using the artificial intelligence plus augmented reality? Well, it turns out, yes, there are quite a bit of applications that are doing this. You know, you can imagine retail being a pretty obvious application. You get cup noodles that have something kind of interesting, lighthearted in this space. Or if you imagine there's different flavors of cup noodles, and you can, essentially with their app, kind of refer to each one of them as a different instrument, maybe a guitar or a keyboard or a bass or something like that. And as you interact with these cups, it'll kind of play a little melody for you. Now, in the sports realm, there's a very interesting application called home court, where if you're shooting baskets from around the three-point line or something like that, wherever you are on the court, it's going to draw little circles underneath you. It'll draw a white circle underneath you where you made the shot, and a red circle underneath you where you missed the shot. So not only is it doing the augmented reality in that realm to project where you were and how well you were doing on one part of the court, but it's also smart enough to do the AI to determine, did you actually make the basket or not? And so this is a really, really cool, novel application, I think, of AR plus AI. And so those are kind of the best ones, I think. And then also you got, in the space of auto financing, incidentally, some of the big auto financiers are actually helping convey information above the vehicles or around the vehicles or whatever you can think of, so that maybe you can go wander the dealership lot any old time instead of having to interact with a salesperson. So let's go over some key terms real fast on this. And we'll start with some of the machine learning side of things. So from this side, we've got the names of various machine learning models that you might use for your image detection or for your object recognition. This consists of MobileNet or SqueezeNet, Inception, and ResNet. So these, in particular MobileNet and SqueezeNet, are very optimized for performance on your smartphone, which is now sitting over there. But as you can imagine, it's obviously very GPU intensive, and the 2 later ones, Inception and ResNet, are very large, and they might have a performance time of maybe a couple of 3 seconds of lag time, possibly you might get, but MobileNet and SqueezeNet might be able to run and say actually the 60 frame constraint to make the application look really, really smooth. But ultimately, these models, whichever one you choose for your object detection task, and you can actually find pre-trained ones so you don't have to worry about training your own. In fact, that's what we're going to do here in this one. Tensorflow Lite is what you're going to feed the model into. Now, Tensorflow Lite is optimized for smartphones by saying, okay, people probably aren't going to want to train a machine learning model on a phone. They're only going to want to run inference, the actual task of the object detection, or the actual task of the classification, guessing, or the forecasting, what have you. And so it's optimized in such a way where really smart people from Google and from academia have come together to work on exactly how to implement which operators are used in a neural network in such a way that it is absolutely taking the most advantage of the graphics processing on your phone, or the GPU that you have. So everything is so fine-tuned that they've been working on these operators for such a long time. It's now become viable to use TensorFlow Lite rather than TensorFlow Mobile into your projects. And finally, in this realm, MLKit, which is an important one. If you don't want to touch models whatsoever, these are actually APIs that you can call from the cloud side or from the local side of your Android device, and it enables specific machine learning use cases on device or the cloud. And so you can imagine the MLKit actually has a really comprehensive computer vision set up in it, so you can do facial detection that will give you like key points of somebody's face, their eyebrows, the tip of their nose, the coordinates of all that stuff. And so you can build maybe an Instagram mustache filter-like thing with MLKit really, really easily. There's also object detection, there's barcode scanning, there's text detection, OCR kind of stuff, and maybe even some safe search types of features as well in MLKit. And so that saves you from any kind of model building whatsoever. Then on the augmented reality side, you got ARCore, which is a cross-platform augmented reality SDK. You can code for it in Android and in iOS. use this OpenGL to perform the tasks you need in order to build up the scene on the phone, such as motion tracking and the scene building aspect of it. And then finally, scene form only for Android at this point is an AR SDK that basically saves you from having to do a bunch of complicated OpenGL interactions that would normally be required to build augmented reality scene. It'll go into kind of calculations of point clouds and things like that towards the end in a little bit of detail. So let's talk about the good stuff. Y'all want to build something with this, right? So here's how to establish your Android app to fuse augmented reality plus artificial intelligence. First things first, let's sit back and, before you even open the IDE, let's install the prerequisites and clone the TensorFlow code from GitHub or get it from Docker, what have you. So the prerequisites you need, not just any old this, but the latest in particular. By getting the latest versions of all this stuff, it'll save you a lot of hassle down the road trying to figure out why this dependency won't work with this library, and this is a bunch of junk. Then you want Java JDK 10, not 11, not 8. Trust me, I've tried all of those things, and only 10 works with the current version of Bazel. Now, it's possible that the new version of Bazel, we might get 11 support, but at the current time, not so much. Now, because I'm a masochist and I see pretty much all of you using Macs, I'm up here with the dorky old Windows PC. You'll need about 5 gigabytes worth of Visual C++ build tools, and this includes a particular flavor of the Windows 10 SDK and the .NET Framework SDK, the two options you'll have to select when you're installing that. And then perhaps a real shell, like MSys2, or you can use git bash. That's also good enough, although incidentally I was able to run the Bazel build through just the basic CMD command prompt with elevated administrative privileges. So I didn't really end up needing to interact with any of the fancy shells like bash on the Windows device. And then finally, pick your place. Where do you want to get TensorFlow from? It's valid to get the source either from GitHub or from the Docker. But if you get the Docker image, you got to get the one tagged Devel, D-E-V-E-L, not Devel like Satan or anything. But you want to get that version so you actually get the TensorFlow code, the source in Python and C++, rather than just the final binary you might incorporate. Then let's actually go into the application code. And I had absolutely no clue there at the time over there. Okay, cool. So let's start with the code root. This is the path to the code that we'll be using for the rest of this example. It's very important that you take this exact one. TensorFlow Lite examples Android app. Because there's also TensorFlow examples Android app, and that's the wrong one, that's old. There's also TensorFlow Lite examples Android Java, which is a totally different Java thing that has nothing to do with anything I'm going to point out here. So it's very, make sure you're absolutely on this one. Now for me, I copied it to a different folder just so I wasn't messing with the original code. Although of course it's easy to track that stuff in GitHub, but then I took it further by breaking some other stuff out, as I'll talk about in a minute. So really fast, adding a scene form dependencies to the Gradle build, and then updating the Gradle build to the latest tools, latest build tools, and then an API level greater than or equal to 26. Now incidentally, this all comes from just the scene form basic code lab that you can find online. So just go Google for scene form code lab, and it'll pretty much explain how to do these hot things. Then also it'll explain how to do adding the augmented reality permissions to the Android manifest file. So you have a couple of lines of code there. And then it'll also guide you into using a fragment rather than an activity to base your application off of. Now, the thing is, by taking this example code from TensorFlow, it's not really set up for fragments, and so you got to do a little bit more work on that end to get that part going. So you can use the, you got to make a new layout and incorporate the augmented reality fragment rather than the original kind of frame layout that it had going on. And then you use this layout in your camera activity file as part of that repo. Or like I did, I made it a separate class, and I had to go refactor a bunch of dependencies on it to use the new class rather than the original one. And then don't worry about the machine learning model assets, because the Gradle build will actually take care of downloading that for you. Now, does anybody want to actually see the lines of code that make this happen, or should I skip over that? Yeah, people want to see the lines of code. All right, then let's talk about the code differences that actually make this happen. I need this one to come forward. Okay, so in the build.gradle, the first thing that gets changed is just the basic things about compile SDK version, build tools version, and then min SDK version. I'll talk about this one later. And then first things first is you're going to implement conduct.AR.scene form. This is all kind of explained in the code lab anyway. And then because it's a fragment and because the TensorFlow code didn't incorporate this originally, also make sure you include the support library for fragments. I just included V4 for the version 28. And then by doing this, it won't complain at you about you included fragments with some weird libraries missing. So nothing super special out of there. Then for the Android manifest, the differences that happen out of here is going to use feature with Android hardware camera AR. And then I took out the whole uses SDK from my version. It didn't really matter for this one, it made it confused. And then also put in metadata Android name conv with ARCore. This is all part of the code lab again, and explain that kind of stuff too. Now the real meat of what I changed for this one is in camera activity. So up here at the top, just importing libraries and taking out ones I don't need. But interesting part is the original code depended on image available listener and camera preview callback. You don't need that stuff anymore because the original activity was building up all these camera previews and getting access to the camera and permissions and lining all that stuff up. And now, because we're utilizing fragment activity from AR fragment, the AR thing is going to handle all the camera interactions for you. So you don't need to worry about all this initialization stuff anymore. So as we go on, just declare some of the variables I need to make sure that other classes can recommend or can access the fragment that I've defined. And then we set the content view to our new Android layout. And so I call this, instead of layout activity camera, there's activity AR. And so the differences in there is that instead of having the frame layout with just camera activity, now it's got a frame layout consisting of an AR fragment plus the overlay view. And the overlay view is drawing the bounding boxes of the objects that get detected on your screen. Now, incidentally, the original camera activity here was dynamically loading up another activity called camera connection fragment tracking. They basically consisted of the same thing. So it would swap out the original demo camera activity for this frame layout, and then that would put in autofit texture view and then a couple of overlay views. And one of these things is just for debugging. So this one didn't really get used a whole bunch. But pretty much you can see that my code looks very similar to what the original layout looked like. Following up that in the camera activity, I've changed around a little bit of code. So set fragment here is now permission acquired. And then I've removed a whole bunch of stuff related to setting up the cameras. And then I kind of put back some of it down here. So what the deal is that you're going to set up basically a callback function. Upon getting a scene from the AR scene view, and then upon getting an update notice from that scene view to indicate that you got a new frame from the camera, basically we're now going to send that frame off to the TensorFlow Lite object detection model. And that's basically what this code is doing down here. You say, is it processing already? Well, if it is, then we'll just discard this frame and go to the next one, or just wait until it's done. Otherwise, if it's good to go, then we're going to basically do some transforms. We're going to do some color space transforms and some size transforms on the picture before we get it ready to send to the model, and we're actually going to go send it to the model. And so that's what that part of the code is doing. And then down here, we basically removed the whole thing about choosing camera 1 API, camera 2 API, so we didn't need that part anymore because we're not establishing that. The AR handles that for us. And then taking out a couple of the abstract functions that no longer get needed. So that is the camera activity. And then, of course, the detector activity is very simple to change. So it's also extending on image available listener. You can remove that, doesn't care. There's an image available, remove some variables you don't need anymore, and then just reference the new class, because I called my multi-box AR tracker, or at the multi-box tracker, then I'm just basically updating all those references. And then this part is basically me just turning these things into lambdas rather than the nasty old Java syntax. So none of this part changes really matter. So, are we all clear on this part? Okay, so let's go down here into videos, and let me show you what it looks like when you run it at this point. This is without smoothing. It's going to flash up a little toast saying the object tracking support is not found. And you can see it's detecting objects, but the colored bounding boxes are all flickering in terms of what color is on what. So basically what this means is as it's detecting an object, it's not tracking exactly where that object's going. in between camera frames. And so that might kind of mess with what you want to implement, because now you're going to have to find out, okay, which object kind of started where and how's it moving relative to each other, how do these things all correlate to each other. Well, the good news is that by using a special library that you can get through a Bazel build, this is why you need to build with Bazel, this will actually be solved for you, so you don't have to worry about coding up a bunch of nasty mathematics and wasting a whole bunch of time doing that when you want to instead be adding mustaches to people's faces. So let's talk about how to do that. So to build with Bazel, this is where you go into your TensorFlow repo. You kind of work your way back through the directory a little bit. You go kind of to the root TensorFlow. And you want to define Android SDK and Android MDK into the workspace, because this is where Bazel goes to refer to libraries that it needs in order to continue the compilation. Then I deleted the API level and build tools version. I kind of confused it. And then I, as I said, CD back to it, and I ran this command, Bazel build, and then the whole path. So I'm actually from TensorFlow directing it to go to this particular Bazel build file that exists in the Android directory. And then it's going to run the job called TF Lite demo. And so I'll show you the TF Lite demo. And then there's also some really funky Windows business. Is anybody planning to do this in Windows? You might be planning on. So there was a really weird thing where, as I downloaded those SDKs and things from that one exe file that I referenced, there was a place where I had to go into program files, like 56, I think, and then you go down to Windows kits. And then in Windows kits, I had to worm my way through some directories. And basically what happened is it installed 10.0.240 through the software tool. But then there's also this reference to 10.0.15063. Well, unfortunately, Bazel only recognizes ladder directory. And so basically what I had to do is copy all the contents of the 240 into the 15.063 in order to fool it into thinking that the files are there, when they're actually not quite the right version. It doesn't have any matter. And remember, you have to do this for the lib and for include. If you're familiar with building C++ applications, you always have to usually mess with both folders anyway, so take that into account. And then basically, once it's all said and done, just pray hard that it works. Because everybody who's messed with Bazel knows that it's very particular about how things go. But if you do get it to work, then you will see a sign of success. And let me tell you, this was a lot of head busting that happened for this part, but unfortunately this is covering it up. But now it says build completed successfully, 280 total actions, and voila. Thank you for your applause. But that's not the cool part. The cool part worth applauding for is going to be back in the videos folder, because let me show you what this looks like when you incorporate that library and build it all properly. So now the Bazel build will put the Android APK usually in some weird folder deep in your user directory. And then you got to go fish it out, and then you can do ADB install to install it on your device. Once you do this, then you find out that it runs like this. No more toes at the bottom. And look at the colors. They're not all jumping around anymore. It's actually doing pure object tracking. And so things are definitely running a lot smoother now. And so isn't that applause worthy? So the next thing we're going to do is add the actual augmented reality code piece into this now. This is where we really start getting down and nerdy with scene form, and really start getting down and dirty with the bounding boxes that TensorFlow Lite is providing us from the object detection that's running. So now at this point, we can't use Bazel anymore. We've done our work with Bazel. We made the TensorFlow, the lib TensorFlow Lite demo.so file, a library file needed for object detection. So basically what you need to do is you need to grab that lib, and this is actually referred to, it's loaded up by the object tracker class. And if it can't find it, then it's basically not going to run the object detection. So you need to pull out this file called lib TensorFlow _demo.so. And this file is also available by Bazel in your, somewhere deep in your user home folder directory on your computer. But basically what you do is you pull it out and you incorporate that model into a directory called source main JNI lib. It goes in parallel with source main Java. And so what that looks like is basically the root of my code in an app source main JNI lives. And then in JNI lives, you have folders that are named after all of the CPU architectures, or maybe whichever ones you want to build for. And the one that matters in this case is going to be the ARM EAVI v7a. So ARM v7 instructions basically are the ones that you want. And the reason for this is because a lot of phones really still support 7. Some of them haven't quite moved on to 8 yet. And actually, for that matter, the library itself is built for version 7. And so I think what actually might be happening is that library code is only usually built for 7 and not for 8 quite so much. When you're looking at all the shared libraries that are available to have. So what then happens is there's going to be one more change to specify in the build.gradle file. So now what you're going to say is that you're going to build the NDK, and you're going to basically build a version for the ARM EAVI v7a. And this is going to be part of your build Gradle file. So this way, if it sees you got a version 8 compatible device, then it's going to put that APK on your phone. Or it's going to look for the version 8 library. It's not going to find the version 8 library. So it's not going to have the object detection tracking capability. So you got to tell it to always go for the version 7. So this way it will find the library on the phone that you're using. And so that's a very important line there to make sure that you remember to get this thing working properly. So now that we've covered kind of the basics of not using Bazel, putting in the correct JNI libs into the correct folders, then let's talk about how to do scene form. So what's interesting is that if you look at the scene form code lab, it's making references to the version 1.4 of scene form UX. Well, unfortunately, when you go to Android Studio, you're going to be downloading the plugin if you go follow their instructions on the scene form plugin. Now it's up to version 1.6, and it'll look all well and good until you go and actually try to run your application and try to instantiate the model. And it's going to say something about this is the wrong SFB file type. We can't do this because it's version 53 and we only support version 52. Well, then you try to go and upgrade your Gradle to use plugin 1.6, and it breaks your scene form UX plugin to convert the model, and so it just becomes a huge mess. I wouldn't even bother with the scene form plugin that you install into Android Studio, but instead what you can do is actually put this step into the Gradle instructions altogether. So in order to do that, it's actually very simple. And what this looks like is down at the bottom. And so basically, you're going to include, now for this part, some of the files will want the apt lib in Android, so put in apt v7. And then I'm going to apply a plugin called Google AR scene form plugin. And this is basically running the same operation that the plugin for Android Studio would do. And so now the Gradle build is going to handle it for you. And so essentially what I'm doing is I'm converting this OBJ object. And Andy.obj is just a model of an Android figurine that y'all are very familiar with if you're Android developers. And then it's converting it into some of the scene form assets. There's an SFA file generated in that folder, and there's an SFB file indicated by the one on the bottom line. And the SFB file is the one that's of the most interest because that's the asset that actually gets pulled in and rendered by scene form. So for all of this having been said, now we can get to the part where we're adding the augmented reality code to the multi-box tracker. And basically, this is also being pulled from the scene form code lab as well. So import, a bunch of imports that you need for this stuff. I changed multi-box tracker to multi-box AR tracker just so that I would still run distinctively. And then define a couple of other class variables. This is where I pull in my Andy.sfb. It comes from the model directory. Now notice that the difference up here when I instantiate, the class constructor now needs a reference to the fragment because this class is normally run as a background thread. And for the augmented reality piece of it, we need to have stuff that runs on the UI thread. And so the fragment can give us access to the UI thread through fragment.getActivity.runUI thread. So from there, go on and just reduce some of the logging and initialize the scene of the augmented reality fragment. And then this is part that's interesting. So now, because this wasn't in the old code, I'll just kind of shrink this back a little bit, make sure y'all can see it good. So running on the UI thread, you got AR fragment, .getActivity.run UI thread, and then basically this part is essentially all the same as what's in the scene form code lab for actually putting object on screen in the spot you want. So it does the hit detection on the plane that's been detected by the augmented reality engine. And then it's basically seeing the bounding box that the object detection model has recognized. That bounding box, the center point of it, is anywhere on the hit on the plane. So it's doing the hit test. And if the hit test passes, it's actually going to place the object in that area. The thing that I added that was a little bit different is that I've got a scene and I've got the node. And what it's doing is it's, first off, it's attaching the node to an anchor node. And then it's putting the anchor node onto the scene because anchor nodes actually really help smooth out any kind of jitters that might happen when you're looking at augmented reality and some of the weird shaking your cameras, or like you twist around a whole lot and sometimes it'll lose track of where it is. And when you use an anchor, it helps with some of the math and smoothing that stuff out. But in particular, what this is doing is it's going to run an overlap test. And I think this kind of comes from helping people writing games that want to see if your character has hit a bad guy and made a collision with him. And so when you do this overlap test, then it's going to see if there's already an Android figurine there. And then it's going to basically remove it from the scene. So it doesn't place down multiple androids. So the hope is that it won't place down a bunch of androids in the spot where it detected an object. But unfortunately what this does mean is that you do have to build up a node, you do have to waste some resources before you can perform the hit test. And so it's there for a split second and then it kind of revokes it out of the scene. So if any of that is clear as mud to you, then hopefully it will become clearer than a bell once you actually see what this looks like. So now what we're taking is opening up the TF AR detection. We're kind of scanning the floor for getting our ground plane. And then we're going to detect some objects. And then we got to align the camera in kind of a special way where the center of the object detection box lines up with our ground plane that's being detected. And once it does, you can start to see the androids pop up. And unfortunately, my little hit test on this one chair didn't quite work as well as I was hoping because it generated 5. But for that one chair on the right, it's still just doing 1. But you can see that it places the object pretty well, nicely on top of the chair. You can spin around and walk around and it makes sense as to where it's going. So what do you think? And so this is proof that at least on my computer in this environment, you can get this to work. So let's finish up here. So you saw the final product, so now it's time to profit. So now that you have successfully built this thing and at least got some kind of proof of concept of it working, now it's time to fix problems that you might have, such as the multiple androids being generated. How are you going to solve that? That's some creativity that you could think of. Or maybe you want to build your own Tensorflow Lite model using some transfer learning, where you take an existing model and you kind of unfreeze some of the top layers of it so that you're removing the essences of the particular pictures that it was trained on. And you're going to train it on your own set of pictures and then refreeze the model so that now it understands the types of objects you want to detect rather than things it was originally trained on. Then, as far as the pitfalls of AI plus AR, one big thing that might happen is battery life. Your device could really take a tank if you're running both of these things constantly. Or you might end up turning the phone into an incendiary device because now you're putting a lot of tax on the GPU, which is both trying to run the augmented reality plus the artificial intelligence. And so one of the things you can do is throttling the artificial intelligence by saying, okay, if the camera's moving around a whole lot, maybe you don't want to do object detection at this point. You can maybe have TensorFlow take a break from the classification and just have the object detection library so we could follow the objects based on the transforms that are happening in the image and based on the accelerometer sensors and the types of other phone sensors that get correlated to each other. So besides that, you're going to want to think about the depth and the size of the object that you are portraying. So if you imagine a chair, for instance, if you want to do object detection on a chair, you're going to build a 3D model that's going to be relative to the size of that chair in such a way that the user is going to scan it with their phone. It'll pop up, and they don't have to really go back uncomfortably to see the whole scene. But now think about using that same model scaled to that chair for a chair inside of a dollhouse. You would end up having that same problem happen where it would scan the chair and the model would come up so big over it, so you really have to lean back and look at the whole thing, and then it would look absolutely ridiculous on top of your small chair. So when you're sizing your object, be sure to do a lot of experimentation to make sure that the 3D object that you put into the scene actually makes sense with what it is you're trying to portray it around. And then also, yeah, basically that kind of covers all the points. And then the other thing that you might want to consider is that my particular algorithm simply uses the center point of the bounding box as the point where I do the hit detection. But if you were to do some clever mathematics, if you knew the size of your object, you might be able to figure out a way to, say, instead of use a corner, or use maybe just the very bottom center, or the top center, or something that made life easier for you to actually have more positive end results of your hit test with the plane. So that, and it might take some knowledge of, well, if I match the bottom center of the bounding box to the plane, and maybe I have to elevate my object maybe 30 centimeters or 60 centimeters or something like that before it actually shows up correctly relative to the physical object that I'm trying to manifest this by. And so it's all going to be kind of open to experimentation, a little bit of light mathematics possibly. Probably nothing as heavy as trying to deal with some of the other things, but sensor drift might possibly be a problem for you as well. So augmented reality relies on point clouds and hardware sensors. And the point clouds are generated by looking for key points of high contrast in rooms, such as corners, or such as complicated patterns, something like that. And so the hardware sensors, if there's not a lot of objects in the room of acute visual interest, are going to be likely to drift with lots of motion. So if you're riding a merry-go-round and then trying to keep track of an object outside of the merry-go-round, it might have wandered off quite a bit. And so any such object anchored to the world space might have this problem. So what's the solution for all this? Well, ensure the scene has good contrast, enough corners to see in every frame something that it can refer to, and something that it can easily glom onto, saying, well, here's this corner. As I move the phone like 5 degrees, you can see it transferring this much, so I must be moving in this manner. Then attach the objects to anchors, as I described. There's an anchor node that you attach the node to. And then be sure to scan enough of the scene ahead of time before drawing the AR. That's where that icon came up with the move your phone around the ground kind of thing at the very beginning. And then you saw it kind of drawing the dots as it understood where the ground plane was in the scene. And then tracking multiple objects can be pretty tricky because object detections that you get from TensorFlow could be missed. You might not recognize an object, it could be false. Maybe it sees a parrot instead of a lampshade. Or it could potentially switch IDs, like you saw with the first example, a whole bunch where the color boxes are all jumping around all over each other. So, as I was alluding to, you want to discover correlations between objects moving on camera. A lot of people do this with pairwise dependencies, which can miss a lot of stuff, especially as objects get occluded by other objects. Also, there's some papers out recently on using non-uniform hypergraphs to do this. Again, very mathematical. So if you want to do research on this stuff, and that's all fine and dandy, but if you like implementations, then why not just spend the time making sure that you build your NDK and libraries properly so that you incorporate this TensorFlow Lite demo library. Otherwise, you're going to have to sit there and really code it yourself. Otherwise, another pitfall is possibly all the resources that's going to be consumed by all those models that you come up. So you're going to have to come up with smart ways to minimize the anchors. You might remember that I was initializing one anchor node to go along with every 3D object node. And so maybe you want to go with one common anchor or just a couple of anchors and then anchor all your 3D object nodes to those anchor nodes instead. So with that, this is it. And I'm going to go pick up the next talk I'm going to attend. Do you have any questions? What's up?
Just two questions. One, can you go over again the reasons for the Bazel build? I just didn't hear that particular part of why that was necessary.
Yes, the Bazel build is building up that live TensorFlow Lite demo.so file, the shared library for the object detection. So if you remember, without that library file being built, it's possible you might just be able to download this on the internet, but then you never know what you're going to get. You might get the wrong processor version, you might get viruses, or who knows what you're going to find when you download a shared library from somebody else. And the advantage of the Bazel build too is that it gives you the APK file, and then you might actually be able to open up the APK file in an archive editor like 7-zip or something, and then go through the directory structure and then find out what versions of processor architecture is built for. pull out the ones you want and then put them in the JNI list folder like I was describing earlier. But recall that without this shared library being incorporated into your app, then you get all these bounding boxes kind of jumping around everywhere. And so it's going to negatively affect the quality of your object tracking. And then as you do put it in, now you notice it understands that how the objects move in relationship to each other. It understands where any one instance of anything is at all times.
Okay. And then the second thing is this particular workflow, would you say, I guess, you can also utilize it within, say, a Unity pipeline if you were doing like a Unity Android Studio Gradle build?
I'm not such an expert on Unity, except the last time I tried to mess with it in the realm of an Android application, I think that if you went back a few years, you'd see that it was a lot easier to incorporate custom Android code into a Unity project, but these days they've got a lot more restrictive on what they'll let you put in. And so it might be a bit more difficult to try it out, but I don't think it's totally out of the realm of possibility, as long as you can include all the libraries you include. Oh, and another thing that I forgot to mention as to why we got to switch out of Bazel and back to Gradle is because if you try to build the whole thing with Bazel, then SceneForm actually has dependencies that you cannot find on the internet anywhere. They're totally undocumented. I don't know where they're coming from. Somehow the Gradle build finds them. And so that's why you got to use Gradle. I'm going to ask the Google people why this is nowhere to be found, how to get the SceneForm stuff to work on Bazel. For now, I don't think it's supported. Any other questions? Did I address your second question wrong?
Thank you. Can you put your information back up there? Because definitely want these slides.
Yeah, definitely. Let me put this up big. So you can see that my Twitter handle is SWebCEO. My blog, because I'm not hip on Medium yet, I'm still on Blogspot. And then you see that it's github.com/nrcity/NL workshop. And then, another thing that I should probably put up is my SlideShare. So I've got SlideShare available. If you look up SlideShare, I'm usually at Stephen Wylie 3, the number 3. Because there are 2 others that beat me to it. But yeah, expect to see these slides up there fairly soon.
Thank you.
Well, thank you. If we have no other questions, then I guess we'll adjourn. You all mingle and find me around lunchtime. I got one.
Yeah, I'll ask you a quick one. So just going off, you said earlier you mentioned Java is kind of like nastier syntax, you're switching to lambdas, and as someone who's like increasing your Java knowledge comes more from like a JavaScript background, it might be difficult with all the stuff going on here, and you're doing like AR, machine learning, and like all these library dependencies and so on. Do you know if there's any way of doing like React Native, or I know like Google has Flutter now, or anything where you don't actually write this in Java, or maybe you're going to go maybe something like Kotlin, or like is it pretty much just lends itself to writing in Java?
It just so happens that my wife is a Google Android expert, a Google developer expert in Android, and so she's not here with me today to vouch for all this stuff. But basically, Bazel currently does not support Kotlin; it only supports Java for some reason. I'm sure they're working on that. And then as for Flutter, I think there's a fellow who's definitely a Flutter expert around here, and he can vouch for, I think that there's something about 3D rendering that doesn't really have an engine for that yet, and so it would still have to borrow some stuff to be able to get that to work, but it would be very interesting to see an example of 3D plus Flutter actually out there. That might be the next thing I work on.
Okay, interesting. Thank you.
What's up, back in the back?
So I've had experience working with Vuforia before, and there's a little bit of description in the speaker series in this event, discussing Vuforia Tensorflow Lite. So I was wondering if you can go over what exactly is the benefits of going for Tensorflow Lite versus Vuforia.
So my experience with Vuforia has been basically, if you imagine kind of object detection as well, then you can use the Vuforia library to basically project something else onto that object. And so you could project something in 3D off of maybe a Dungeons and Dragons type of map that you've got. You could also imagine maybe having a frame of a commercial put up somewhere, and now it pops up the whole commercial and plays it in that realm. And if you adjust the frame, you can rotate it upside down or or shift it and skew it, whatever, and it'll still actually skew the thing on top of, like it'll play the video in that same type of aspect, I guess, as you're looking at that frame. So I think that Vuforia is good for when, it's a very good one, I think. And so it's good for when you want to build something, especially in Unity, just really quick. If for some reason you need more control over what you're doing, then you want to switch to TensorFlow Lite. Like for instance, if there's, I think Vuforia, you can actually train it on whatever types of objects you want anyway. So you can have, predefined model of, I'm going to look for a dog, I'm going to look for this weird hexagonal shape with a bunch of patterns inside of it. But I think that over time, you do have to pay some money to them to put in a whole bunch of objects, possibly if you want. So yeah, when you start thinking about it from the enterprise perspective, sometimes you want to kind of rack it back and have control of your own code. But yeah, I'm glad you mentioned that because I'm trying to think about the thing that could also kind of do this stuff. And yeah, it's Vuforia. So if you're interested in checking that out, you should check that out as well. It's Vuforia. All right, well, if there's any further questions, then you know what I'm wearing. You'll see me at lunch, I guess, and I'll let you all go.